Okay, so good morning, everyone. Let's start with today's lab assignment. We'll be working on lab number 5. Okay, so this is lab number 5 instruction. So the goal of today's lab is to practice the interpolation of data points. So in practical, when you are given a set of data points, you would want to find a function that fits all of those data points. And the process of finding that specific function would be called interpolation. And we would use MATLAB tools to help us do those interpolation stuff today. Okay. And these are normal things. So the first part of today's lab assignment will be about polynomials. So in MATLAB, we represent polynomials with the vectors of their coefficients ordered by decreasing power. So suppose Px is equal an x to the n plus an minus 1 x to the n minus 1 up until a1 x a0, then the coefficient vector should be an minus 1 up until a1 a0. Okay, the vector is represented this way. This is a column vector, okay? But as you can see, the coordinator states that MATLAB doesn't care if this is a row or a column vector. So it can either be a column vector or a row vector. And in order to transform, in order for the MATLAB to understand we are using this as the coefficient vectors for a polynomial, we would use the command polyval. So this is the polyvalue, okay? So polyval can be used to efficiently evaluate a polynomial Px as a particular value. So for example, if we want to evaluate the value of the polynomial 3x to the 5th minus 4x cubed plus 2x plus 1, we would create the vector of coefficient. So as you can see here, the highest exponent of x is 5. So we got 3. Then we don't have any x to the 4, so we should have 0 next. We got negative 4x cubed, so we got negative 4. We don't have x squared, so once again 0. And we got 2x, 2, and finally 1 is the constant coefficient. Okay, so in order to evaluate the value of this polynomial at x equals -2, we would use the command polyval p -2, and the answer is -67. So -67 is the value of this polynomial when we evaluate that at x equals -2. So that's basically what this command helps us to do. And also the polyvalue command not only can help you evaluate the value of the polynomial as one single number of x, it can do that for numerous number of x at the same time. So for example, here we are using the polyval. So as you can see from this command, we got two parts. The first part is 1, 0, -1. This represents the coefficient vectors for the polynomial. So in this case, we should have x squared plus 0, x minus 1, aka x squared minus 1. And here are the value of x that we would want to evaluate the polynomial at. So you should see that this is a 2 by 2 matrix, okay? Because we got a semicolon here. So this is the first row and this is the second row. So the answer is also a 2 by 2 matrix. And here, this number 3 is actually the value of the polynomial when we evaluate at this first component 2. And similarly, for the second component of the first row, this 0 is the value when we evaluate the polynomial at -1 and so on, similar for the other component. Okay, let's move on to the test. Consider following the set of data points in the XY plane. So here we got 1, 2, 3, 4, 5, 6 data points in total. You will need to find a polynomial of degree at most 5 that passes through these 6 points. Does this polynomial exist and is it unique? Okay, so the answer is yes. We answer this question on chapter 1 of the lecture when we talk about polynomial interpolation. There is one specific theorem saying that if you are given n plus 1 data points, then there will be exactly unique one polynomial of degree of maximum n such that it will pass through all these data points. So because here we got 6 data points, so the degree of the polynomial is at most 5. Okay, it is exactly according to that theorem. So the answer is yes, but once again, this is not a question in this assignment that you need to submit, but I just want to clarify this. So the first task is to create 2 row vector x and y containing respectively the x and y coordinates for the data points. So for the vector x, we would need to have all the x components. So we should have -2.1, -1.3, 0.1, 0.5, 1.4, and 2. So let's put that on here. So here we got x, and yeah, I don't remember the number. So first, -2.1, -1.3, 0.1, 0.5, and 1.4, 2.0, 1.4, 0.0. Okay, this is x, and we would do the same things for y. So here we should have 2.2, 5.1, 2.2, 5.1, -1, 0.1, 0.6, -1, 0.1, 0.6, and last but not least, 1.8. I'm gonna run this. Okay, so because I am using a semicolon here, so it does not show x and y, but as you can see here, the x and y variable show up on the right column. So we did correctly. Okay, so that is the first task. On the second task, assuming there exists a degree 5 polynomial which passes through all the points in, okay, all the points here, all the points in star. Okay, so write out a system of 6 linear equations representing this information. Each equation in the system shows that one pair belongs to the function. Okay, you don't need to submit this task. So we got 6 data points in total, but I'm just gonna do one for example. So suppose, okay, so because Px is polynomial of degree 5, so I'm supposing that it will have the form of a5 x to the 5th plus a4 x to the 4 plus a3 x cubed plus a2 x squared plus a1 x, and last but not least a0. Okay, a0, I'm sorry. So in order for this function of for the graph of this polynomial to pass through the first point, aka -2.1, 2.2, it needs to satisfy the following formula. When we replace this x by -2.1 and this y by 2.2. So the first equation should be 2.2 equals a5 multiply -2.1 to the 5th plus a4 -2.1 to the 4 plus a3 -2.1 cube plus a2 -2.1. Oh, I'm sorry. -2.1 square a1 -2.1, and last but not least a0. Okay, so this is basically the first equation in the system, and the remaining 5 equation is similar, so I'm not going to do that here. I just want to show you some example. So this is the system. Okay, so that is for task number 2. Moving on to task number 3. Create a variable holding the coefficient matrix A for the system in task number 3. Task number 2, do not enter the matrix entries by hand. Instead, initialize a 0 matrix with the appropriate dimension using zeros, and then fill the coefficient using a pair of for loops. So your code would be something like this. Okay, so let's first talk about this code over here. So first we got n equals the length of x. So this will help determine the size of the matrix that we are about to put in. So A is the coefficient matrix, and it should be of the size n by n. So that's the reason why we should determine the value of the length of x first. So in this case, the length of x is actually 6 because we got 6 data points. So we should expect n to be equals to 6. And here for the zeros command, it will create a zero matrix of size n by n. So here we should have a 6 by 6 matrix, a zero matrix. Then we would use a loop. So for I equals from 1 to n and for j equals from 1 to n, ij equals. So this loop represents the I in the loop will represent the row and the j will represent the column. So using these two loops, we can put on all the value of the matrix without having to put the number by hand. It will be a lot more efficient. Okay, so let's put these on first. I wonder if we can copy this. Let's try. I haven't tried this. Oh, yeah, we can do it. Okay, so I need to make some adjustment. So this for loop is inside this for loop, so you should put some space here. Oh, sorry. Okay. So all we need to do now is to change this part. So let me help you with this one. So let's start with the first component of the first entry of the matrix, the A11. So as you can see, the A11 should be this one. It is negative 2.1 to the power of 5. Okay, so what is the number of negative 2.1 comes from? It is actually the first component of the x vectors. Okay, so you should expect this. And because in general, we are in the I row. Okay, we are in the I row. So this should be xi, the I component of the x vectors. What about this number 5 over here? So remember, I told you that j will represent the column. So we are dealing with the first column, but the exponential is 5. So what is the relation between 5 and 1? Their sum is 6. Okay, the sum of 5 and 1 is 6. And what is 6? 6 is actually n here, the length of the matrix X. So here we got the column j, and from j, in order to achieve the exponent, I'm just gonna take the exponent of 6 minus j. Does that make sense? Okay, so if you do the same stuff for the second component, aka 1, 2, here you see that this is 4. So 4 is actually 6 minus 2. So this should be the correct one. Okay. So let's run this. So everything is good. You can see the matrix A show here is a 6 by 6 and n is 6, just as our prediction. So it's okay. Now we got the variable A. If you have completed the previous task correctly, you will have generated the coefficient matrix for A for your linear system from task 2. Notice that the constants from the right-hand side are just entries of the row vectors y. Okay, so here we got 2.2, negative 5.1. Yeah, it is exactly the component from the y vector. So we don't need to put any more vectors here. We are just going to use the y vectors here. And let me check if there is some. Okay. So the system using the MATLAB's backlash operator. Okay, so remember from the previous lab assignment, there are actually 3 ways that we could use to solve for a system of linear equation. The first, probably the most efficient one is the one to use the backlash. Okay, but remember the backlash. So normally we would put the backlash like this one. This is the coefficient matrix, and this is the constant, the constant vectors. But remember, in order to use this operator, this constant must be in the form of the column vector. Okay, remember, in order to use this operator from MATLAB, this constant vector should be in the form of a column vector, but here y is a row vector. So in order to transform from a row vector back into a column vector, we are going to use the transpose operator here. Okay, so a backlash transpose of y. And here, okay, the coordinator wants us to name the solution P. So here we should have P equals this. Okay, let's try to run this. Oh yeah, there's a typo here, sorry. So you should see this is P. This is the coefficient factor for the polynomial we have found. Okay, so we complete this test. Okay, at this point, it would be a good idea to compare the values of the polyvalue P at X with the vector Y to make sure you got the right answer. To do this, add the following to your script. I'm just going to copy this. Okay, and I'm gonna run. Yeah, I think. Okay, because we copy this from the PDF file. Let's check if we make some mistake. Okay, so this one. Should. Okay, so let's rerun this one. Okay, so you should see the max error is 6 point something e to the negative 15, meaning that it is 6 multiplied 10 to the negative 15. So it is really, really small. So even though it is not zero, but we can expect to have a correct polynomial interpolation because of the error in MATLAB itself. It is not our fault. Okay, so this is correct. And moving on to the next task, now we should divide the interval from negative 2.1, negative to 2.0 into 100 equal intervals using the linspace command and store it to the variable x1. X1 should have 101 entries. If you haven't worked with the command below, see if you can figure out what the following commands do. Okay, so you can follow the step, put those command into your MATLAB, or you can find another way to do that, which is to okay, which is to go to the MATLAB website and put on the search here. So I'm just going to put the linspace here to see what it gives us. Okay, so this is linspace. So we are actually interested in the second formula. I'm just going to click here. So linspace x1, x2, and generates endpoints. The spacing between those points are equal to each other and equals to x2 minus x1 over n minus 1. Also, okay, so get back to the task because we want 100 equal intervals, meaning that we need 101 entries, 101 points. So negative 2.1 should be x1, 2.0 should be x2, and the remaining value should be 101. So in this case, x1 is equal to linspace of negative 2.1, 2.0, and 101. Okay, and let's run this. So as you can see on the right column, x1 is 1 by 101 matrix. It shows that this is a row factor of 101 component. So this command is correct. Now moving on to the next one. Evaluate the polynomial at the points of x1 and store the result to the variable y1. So we discussed this earlier in the first part of the segment. In order to do that, we're simply going to use the polyval command. And in order to use this command, we need to put two things. The first one is to put the coefficient vector of the polynomial. So here, that should be P. And the second part is to put the value that we want to evaluate. So here we should put x1 and run. So as you can see, y1 has the same size as x1, so it should be true. Okay, it is correct. So we finished this step. Cool. So in applications with many data points, polynomial fitting is often not a practical for a number of reasons. In those cases, other methods of interpolation are used. There are several methods of interpolation available in MATLAB, and we will consider the most commonly used, which is linear cubic, piecewise cubic Hermite interpolation and cubic spline interpolation. So I will slightly explain what these method will return when you use them. So I'm just gonna put interpolation method here. So here we got several methods that MATLAB can help us to use. So the first one is the linear. So what it gives us. So description linear interpolation, this method fits a different linear polynomial between each pair of data points or curves, or between sets of free points for surface. So let's leave out the part where it talk about surface because we are working in XY planes, one dimension. Okay, so it will return a linear polynomial. So linear polynomial, aka a linear function y equals ax plus b. And we should know that a linear function, the graph of those functions is simply a line. Okay, so this function, this method will simply connect those data points using lines. Okay, so it will connect the first data point with the second data point using some segment. Then the same things happen for the second data point and the third data point. Simply, it connects all the points using segments and lines. Okay, so that is the first method. The next method is the cubic spline. So this method fits a different cubic polynomial between each pair of data points for curves. So it is quite similar to the linear method, but the different part is that instead of using a linear polynomial, it is using a cubic polynomial. So cubic polynomial is polynomial of degree at most free. Okay, so it can either be a line if the cubic polynomial turns out to be a first degree polynomial, so it depends on the data point. But this is the cubic spline. And another method that was mentioned in the lab assignment is this one. So in this help section of MATLAB, it is called the shape preserving, okay, or aka piecewise cubic Hermite interpolation, PCHIP. This method preserves monotonicity and the shape of the data. Okay, so this method acts similarly to the cubic spline method because it also uses cubic polynomials in this interpolation, but it is more accurate than the cubic spline because it preserves the monotonicity and the shape of the data. So what is the monotonicity? The monotonicity is whether the function is increasing or decreasing. It will preserve that. And it will also preserve the shape of the data. So it means that when we talk about the function, sometimes there will be something called extremum or the local maximum or the local minimum. So it will also preserve that. So the shape of the data point will not change if we use this method. So basically, these are the three methods that we are going to use. We are going to implement today. Okay, get back. So, and in MATLAB, in order to use the interpolation, we would use a command called interp1. Why one? Because we are working in one dimension. If we are working in two dimension, it will be interp2. Okay, so once again, let's get back to this help section and put that interp1. Okay, so interp1, because we are using different method here, so I am interested in the second command. So we will need to put 4 parts into this command, xv, xq, and method. So the method can either be linear, nearest, next, previous, PCHIP, cubic, blah, blah, blah. And the default method is linear. And what is xv and xq? So xv, xq returns interpolated values of a 1D functions. The x contains the sample points and v contains the corresponding values. So in this case, basically x is the x vectors and v is the y vectors, the x component and the y component of the data points. And xq is the coordinate of the query points that we want to evaluate the value of the polynomial. Okay, so let's do this. Okay, so we are using the exact x1 variable that we have just create here the row vector including 101 entries. So we don't need to create any more. Now let's get to the task. So use the inter P1 to compute the values of Y2 using the linear method, using the cubic method, and using the spline method. Okay. So this is Y1, Y2 equal inter P1 X, Y, X1, and here we are using the method linear. Okay. And similarly for, oh, I'm sorry, there is no zero here. For the next one, I'm just gonna copy and make some adjustments. So Y3, Y4. So we are using the same command, but we are changing the method. So instead of the linear, the next one is the cubic method. And the last one is the spline method. Okay, let me explain a little bit to you. So in the newer version of MATLAB, actually the name of method is changed into cubic method. However, because we are working with the older version of MATLAB in the 2019, so the name of the method is still, if you remember from this one, okay, let me get back to you. So remember the name of the method is, it should be pchip instead of cubic because we are working with an older version of MATLAB. So if I just put cubic here, you will see it will show some problems. So let's try to run this one. Okay, so you can see wanting cubic will change in the future release, meaning that in the newer version of MATLAB, it will actually be called cubic. But now because we are working with the older version, you should use the word pchip instead. So I'm just gonna put pchip here, pchip. Okay, and let's run this again. And everything works perfectly fine. Okay, so we're done with the task 7, 8, 9. Now for the final task, the coordinator wants us to plot these functions on the same graph using the plot command, and there might be some description. Use black color for Y1, blue for Y2, green for Y3, red for Y4, and mark the initial set of points storing X and Y on this graph using black circles. The result should look like this. So, okay, so if you're not remember how to use the plot command, you can always come back to the help windows in MATLAB and put on plot. So here, plot. So the most simple command of plot is simply plot X and Y, where X is the X coordinate of the data points and Y is the coordinate of the data points. But here we need some more description. We want colors and marks and stuff. So you would want to go up into this part where when we talk about the line style, Okay, so you can either use this style, it will be dashed, or you can either use this one, the colon one, or you can either use this one. So G stands for green, right? This one, meaning that we are using the color blue, the dashed line and the circle mark at the data point, as you can see from the example. Okay, as you can see from the example. So that is what we're gonna do. So in order to use plot, first of all, you will need to put the figure command on first. Then I would use plot. Okay, so first of all, we are going to plot X1, Y1, and the coordinator one is to be flat. So X1, Y1 flat. Okay, so let's try to run this one. Run it. So here, this is Y1. Okay, next, we would do the same things for X, for Y2, Y3, and Y4. So we should have X1, Y2. Now he wants that to be blue. X1, Y3 to be green. And also x1, y4 to be, red. And now let's run this once again. Okay, so this is what we have. So if you compare this to the final picture from the lab assignment, you should see that there are two different things. So we haven't put the box circle on the initial data points. And also, as you can see, the axis here, the x-axis to be specific is only from -2.1 to 2. So in order to restrict the limit of the x-axis, I am going to use another command, which is called x-limit. Okay, I am going to use a command named x-limit. So inside, you should put the interval of limits that you want to restrict your x-axis to. And here I am interested to restrict the x-axis from -2.1 to 2.0. So that's what I'm going to put here. And in order to mark the initial data point, we are going to use plot once again, but here we are plotting xy because xy is the initial data point. And we want it to be black circle. So it should be black O like this. Okay, so let's try to run this one more time. Okay, so as you can see here, we see that it does not change the limits. I think it is because of the program, because I tried it myself yesterday and I also encountered the same problem. And when I close the program and I open that once again, it solves the problem. Trust me. Okay. Okay, so let's try to run this once again. Run. Okay, what is? Okay, I don't know what happened, but yesterday I did the same things and it showed the same exact result like this picture in the lab assignment. Yeah, you can try to run this code several more times to see if it changed anything. I don't know. I think it is. I put this below the plot. Okay, I think. Oh yeah, I believe it should be. Yeah, I'm sorry. It should be under the plot command instead of below, before the plot command. So as you can see, this is exactly the same as the picture the coordinator shows in the lab assignment. Okay, so now let's examine a little bit this picture. So as you remember, the first one is the polynomial interpolation. It is a polynomial of degree 5. So as you can see, the function is the smoothest one out here, out of the all interpolation. This is the smoothest one because it is actually a polynomial. Okay, now moving on to the next one, the blue one. This is the interpolation using the linear method. And I just explained to you that the linear method simply connect all the data points using segment. So as you can see, we got one segment, two segment, three segment, another segment, and another segment here. Moving on to the green one, here we are using the P-chip method, the P-chip method. Okay, and the red one is the S-spline method. So as I already explained, these two methods are pretty similar, but the P-chip method is a little bit more accurate because it will preserve the monotonicity and also the shape. So what is the difference between the red one and the green one? So as you can see here, from the initial data point, this should be a local maximum, right? This point x -1.3 y equals 5.1 should be a local maximum. And in the green one, it also show the same. It is still a local maximum. However, in the red one, the local maximum is somewhere here. So as you can see, the green one is more accurate in terms of interpolation compared to the red one. And anything else stay the same. So as you can see, it should be a local minimum, and the green one still shows that, but the local minimum of the red one is slightly on the left. Okay, so this is basically all the interpolation stuff. And yeah, and that is the end of this lab assignment. Do you guys have any question? Okay, so glad to hear.